ROS2 includes the incredibly powerful TF2 library that handles transformations between different frames of reference on your robot. It's useful when you have different parts of a robot moving independently or multiple robots interacting with each other. It also provides a foundational building block for libraries that tackle more advanced problems like simultaneous localization and mapping, or SLAM. Previously, we looked at the TF2 library in ROS2 and talked about how it's helpful for transforming coordinates between different frames. We're going to continue that discussion and build out a full example that uses both broadcasters and listeners to give you a sense of how the TF2 library works. Here is a quick recap on the concept of frames. Most robots operate in a real or simulated environment, the space around them, and they need to interact with it. Let's say we want to drive our robot toward a target. The robot can have a position and heading in the environment, which we'll call the world frame. Frame is short for frame of reference. This is a coordinate system relative to that particular environment or object. The robot has its own frame, an origin and set of axes relative to the robot's body. You can have sensors or manipulators that move relative to the robot. So you might use the robot's frame to make those adjustments, but sometimes you want to translate between the robot's frame and the world frame. For example, you might want to angle the robot toward the target, knowing the sensor is offset from the robot's body. This is where such translation or transform comes in handy. This is a simple example, but you can probably imagine things become more complicated when you start introducing multiple moving components, like a manipulator arm with many actuators. The TF2 library helps us translate between these different frames to do things like plot paths for our robot and its various parts. We're going to use turtlesim to have one turtle follow another. In this case, we'll control turtle 1 and have turtle 2 automatically follow turtle 1. Let's say we want to do this in the world frame. We'd first need to calculate the x and y differences between the turtle positions. In turtlesim, turtles are moved by providing a linear velocity and an angular velocity. So we need to get the distance between the turtles by using the Pythagorean theorem. This acts as our positional offset or error. We then need to figure out how much turtle 2 should turn to face turtle 1. We get that by using a little trigonometry. We'll take the arctangent of dy over dx and then subtract turtle 2's heading from it. That should give us the difference between the heading and vector angle pointing at turtle 1. From there, we use the first part of a PID controller to assign our linear and angular speeds. We just use the proportional part and figure out some constants for the KPs to make the turtle move in a relatively smooth fashion with no overshoot. I recommend checking out my PID controller videos if you'd like to learn more about the specifics. This is relatively straightforward using just the world frame, but as a demo, let's do this exercise using TF2. Rather than calculate everything in the world frame, we'll do it from turtle 2's frame of reference. Our coordinate system is now rotated from the perspective of the world frame, and the origin is offset. In turtlesim, the turtle is always at the origin and pointing along the positive x-axis in its own frame. So we first create a listener that translates the position and orientation, known as pose, of turtle 1 in turtle 2's frame. With that, we can get the x and y distance to turtle 1 from turtle 2. Note how the x and y lines are rotated. They are now drawn from the turtle 2 frame instead of the world frame. We'll use the same proportional controller as before. The distance is again calculated using the Pythagorean theorem. This time, we don't need to subtract the vector angle from the absolute heading of turtle 2. Because turtle 2 is always facing along its own x-axis, the angle offset is just given by the arctangent of dy over dx. We now have enough information to feed our proportional controller to steer turtle 2 toward turtle 1. This will require using broadcasters and listeners to set up a frame tree in TF2. We'll use the broadcaster we wrote in the previous episode to provide transforms from the world to turtle 1 and from the world to turtle 2. This time we'll write a listener that gives turtle 1's pose in turtle 2's frame of reference. We'll use that information to drive turtle 2 toward turtle 1. Yes, it is more code than doing everything in the world frame, but it should give you an idea of how TF2 works and give you the building blocks for scaling up to large, complex robots with lots of moving parts. Let's go into VS Code for ROS2. We're going to make this a little bigger. Yes, I trust the authors. Let's minimize this and go into source in our workspace. Let's go into my Pi package, which is where we've been working for this TF2 example. Let's go into here and let's review this broadcaster that we created in the previous episode. This broadcasts a transform. Think of it like a special type of publishing on a topic that TF2 knows what to do with, and it will broadcast from the world frame, in this case by default, to the child frame, which we default to turtle1. Notice these are parameters, so we can pass in a different child and parent if we want to. It creates a subscription to the pose that turtlesim constantly publishes. So every time turtle1 gets a new pose message published to that particular pose topic, this will call this broadcast callback, where it will get the timestamp. It will set the parent ID to parent and the child ID to child, and it will get the X and Y coordinates in the world frame, and then it will get the heading of the turtle from this message.theta, convert the Euler orientation that's in radians to quaternion, which we then set the X, Y, Z, and W components. It then sends out that transform using this special TF2 broadcaster, and then we just run the node. We're going to use this on multiple turtles, and we're also going to create a listener that performs the transform and then has a turtle2 chase our turtle1. Let's create a new file in my Pi package. We'll call it TF2 turtle listener. We will import math as we need that for some computations later. And then we will get the 3 boilerplate imports that we've been using, rclpi, rclpi.executors, we'll get that external shutdown exception. And then we will get node from rclpi.node. We also need to import the twist message interface that comes from geometry messages. And we need the TF2 library that comes with ROS. Let's define our class. We will call this turtle follower. We will use the TF2 listener in here to plot a course for this particular turtle and have it track the main turtle. We then set up our constructor where we call the superclasses constructor with the name of the node, in this case, turtle follower. Next, we will declare a few parameters. We will declare the leader, which turtle this turtle should be following, the follower we want to control, and a timer period, how often the command controls are updated for the follower turtle. I'm going to zoom in here, so hopefully you can see what I'm doing a little better. And let's scroll down. Then we're going to get those parameters and set them to the various member attributes. So we will do one for leader, we'll do one for follower, and we will do one for the timer period. Then we will create a publisher. This will use the twist interface. We will publish to the name of the turtle. In this case, it should be the follower, so turtle2 by default, and the command velocity topic. By publishing 2 here, this will allow us to control turtle2, and then we will set the buffer size to 10. This is where we create our TF2 listener. So the first thing we need to do is set up a buffer. TF2 will use this buffer and fill it with transform information that it receives from all the broadcasters. And it will use this buffer to look up the transform between any 2 frames in that full tree that we've constructed. Once we have that buffer, we need to create our listener. In the TF2 ROS library, there is this transform listener object. We initialize it with the TF buffer we just created, and then we need to pass in this object, this node we're working in. Next, we will periodically call the follow function by creating a timer. We will set the period to the value we got from our parameter, and we will tell it to call the follow function that we will write in a moment. I'm going to go ahead and set self timer to be marked as a private member attribute. Once the node is set up, I like to make a note to the console that we have started the node, and we will print out which turtle is following which other turtle. In the follow method, we will periodically steer the follower toward the leader. Remember, this gets called about 10 times a second, unless you change that parameter value. So in here, it's usually good to use a try catch block or try accept block because sometimes the transforms fail in the TF2 library. And this is where the magic of the TF2 library happens, this one function. We've done all this setup to create broadcasters between frames and create that listener So now we go into that buffer object and there's a lookup transform method in that object where we tell it which frame we want to transform to, which frame we want to transform from, and give it a time. So now we have information about the location of the leader turtle, so turtle 1, in turtle 2's frame of reference. We no longer need to do things manually from the world frame. We can use the transform object, that TF object we just created. That will have information about the translation between the two different frames. So if we get to the .x and .y, those are the differences in x and y from the follower to the leader. Then we compute the arctangent, just like we saw in the slides, to get the angle between the follower and the leader in the follower's frame. So that will be math.atan2, because we want to use the arctangent 2 function that comes built in with Python, and we will say dy, dx. Then we will set up our message that we will send out to that command velocity topic. Twist.linear.x is the velocity that we want the turtle2 to drive forward at. So we will give it 2.0, that is a constant that we've hard-coded here, times math.square root dx squared plus dy squared. This square root of dx squared plus dy squared is the Pythagorean theorem. That is the distance from the follower to the leader. We multiply that by 2 because that distance is the error, and this 2 is the PID controller constant only for the proportional controller part. As I mentioned in the previous episode, if you'd like an overview of PID controllers, check out my 2-part series on getting started with PID controllers. We only need the proportional part here as it's simple, and I'm just hard coding it here because I've already gone through the effort of tuning it, and 2 seems about right. It's also what ROS uses in their examples. Then we will say twist.angular.z. So remember that the turtles only have 2 controls. The velocity in the forward direction, which is along its own x-axis in its own frame of reference, and then an angular velocity of how much to turn by. In this case, if you recall, from turtle 2's frame of reference, the angle between it and turtle 1 is the error, how much it needs to turn by in order to face turtle 1. So again, that's just a PID controller. We're going to only use the proportional part here, and it's already been tuned for you, so we're just going to say 4 for that proportional constant. So now we have a very basic PID controller where we get the distance and angle errors from the frame of reference of turtle 2. With those, we just published that twist message, and that should control turtle 2. We will catch any exceptions that happen. In this case, we will just print it to the console and say we could not perform the transform. Then we will write that boilerplate code we've been working with for pretty much all of these nodes in Python, where we define our main function, which will be used as an entry point. We will initialize and run the node, create that node, which we called turtle follower, go ahead and run it. When we exit, usually with something like Control-C, we will shut it down nicely. So as long as node is running, we will destroy that node. If RCLPy is also running, we will shut that down. And if Python is executing this file directly, go ahead and run that main function. Looks like I forgot a colon here, and that should be good. I'm going to save this with Control-S. We should not need to add anything to package.xml as we already have our ROS package dependencies listed here, specifically turtlesim and TF2 ROS. If we go to setup.py, we do need to add our executable. We will say the executable of TF2 turtle listener is equal to mypypackage.tf2 turtle listener and the main function in that file. Let's save this with Control-S again. We need to go to View. Let's go to Terminal. Make sure you're in the workspace directory and say colcon build, packages select, mypypackage. With any luck, that should build. Now let's go over to our run desktop. Let's bring up our first terminal. We will run turtlesim and the turtlesim node in that. Let's move this turtlesim over here. Let's go to File, Open Tab. We will run the teleop here as well. And now we can drive the turtle around with our arrow keys. Let's open up this other terminal. I'll put it down here so you can see what's going on in turtlesim. Navigate into our workspace. Don't forget to source install setup.bash. And we need to run our TF2 turtle broadcaster, like we saw in the previous episode. So that's just broadcasting from the world frame to turtle1 in the background. Let's open up a new tab. If we say ROS2 service list, if we scroll up, you can see all of the available services that's part of turtlesim and our turtle1 that's being run. This is where we can spawn and get rid of turtles in turtlesim. We can also reset and clear the map. Let's get some information on that spawn service. You can see it uses this message interface of turtlesim service spawn. And if we look at that interface, you can see we have to give it an XY theta. So that's position, heading, and we can optionally give it a name. Otherwise, turtlesim will automatically assign a name to it, like turtle2, turtle3, and so on. So let's try calling that spawn service. We will say ROS2 service call /spawn. That's the service name. We will give it the interface turtlesim serve or service spawn, and then the information that it's requesting. So X we will say 2, Y we will say 1, and theta we will say 3.14. When that's called, you should see a turtle appear in the bottom left area of turtlesim. It should be facing the left direction because 0 is to the right and pi radians is to the left. And you can see that it's automatically been given the name turtle2. If we say ROS2 topic list, you can see that we have our turtle1 namespace with the topics in there, and we also have the new turtle2 namespace with the very similar topics. So this is how we can control turtle1 versus turtle2. We can also get poses of both turtle1 and turtle2 in their separate namespaces. So if we go back up to teleop, you can see we can drive turtle1 around, and turtle2 just sits there. Let's go to config workspace. We will source install setup.bash. In addition to the turtle1 broadcaster, we need a broadcaster for turtle2. So we need to make sure we construct that tree fully where we have a transform between the world frame turtle1 and from the world frame to turtle2. So both broadcasters need to be running for that listener to operate correctly. We get that by typing ROS2 run mypi package TF2 turtle broadcaster. This is the broadcaster that we wrote in the previous episode, but we're going to say --ROS-args, set the parameter child to turtle2. Remember that the default of the parent is still the world frame. So let's run that. And now we have a broadcaster going from the world frame to turtle2. So now that tree has been constructed and our listener is ready to go. Let's create even a new tab since we have the two broadcasters working on tabs 1 and 2. And just so you can see how those frames are working, let's call this ROS2 run TF2 tools view frames. This will construct a PDF for us that consists of that graph. So if we go to Applications File Manager, we can go into our workspace. And let's take a look at frames. We will open it with Firefox. Sure enough, we have our broadcasters going from the world frame to turtle2 and from the world frame to turtle1. So both broadcasters do appear to be working. We can close out of that, close out of this file browser. Now we're finally ready to run our listener or our follower that has the listener in it. Make sure you are in the workspace. Go ahead and source install setup.bash, and we will call ROS2 run mypi package TF2 turtle follower. If you remember, by default, the parameters are set such that this will control turtle2, telling it to follow turtle1. So let's go ahead and run this. No executable found. Looks like I called that follower on accident. I'm going to change this to listener because that's what we actually called the file. Let's run this. And it looks like I've got an error in my code. If node is not none. Let's take a look at our code. Okay, it looks like I forgot a comma in my code here. So follower turtle2. This was throwing an error in the runtime. Follower turtle2 doesn't really exist as a parameter, and that didn't work here. So let's go ahead and save that. Let's rebuild my package. Looks like it built. And let's try running that node again. There we go. As you can see, turtle2 zoomed over to turtle1. So let's go to our teleop and let's drive turtle1 around. And you can see that turtle2 tries to keep up with us. This is a fun little demo showing you how TF2 works so that you can create transforms between any frames of reference in your robot or fleet of robots. We do not have time in this series to demonstrate TF2 in C++, as I wanted to focus on the concepts, and Python keeps it high level. If you would like to see an example of the broadcaster and listener in C++, check out the GitHub repository for the course. Feel free to dig through that and run it. Your challenge, should you choose to accept it, is to expand the broadcaster and listener example to work with any number of turtles. The catch is that each turtle must follow the one in front of it, maintaining a little bit of distance. This should create a train of turtles as you drive turtle 1 around using teleop. I recommend putting this in its own separate package and consider making a bring-up package to go along with it. This will allow you to launch the full application with one terminal command. Good luck with the challenge. I recommend spending some time on it as it will test your knowledge of TF2, parameters, and launch scripts. With that, we are done discussing the main parts of ROS2. By now, you should have a decent grasp of using nodes, topics, services, interfaces, parameters, launch files, and TF2. There is so much more in ROS, but this should be a good start. The one thing we did not touch on is actual hardware. On its own, ROS does not really provide interfaces or libraries to hardware, which means we have to integrate that ourselves. So in the next episode, I'll demonstrate how you might do that with a simple rover-style robot. Stay tuned.